Alright, so you struggled a while with getting these if statements to work, and it's not the easiest. I can show you here like a small test I did just on this graphical interface. Put the header mark on the first qubit, and so it will be in state plus. And then I do a measurement, and okay, I put a barrier here to make sure that the next things happen after this measurement. And then I put an X here, and then I've dragged an if to it, which is why you get these two equal signs here. So this X operation will only be performed if the state for this classical register is 0. That is, if we have measured 0 here. So you can see it maybe more clearly in the casting code. So if classical register is state 0, do X on qubit 1. And then we measure qubit 1 as well. So what should be the result of this circuit if I run it? Yes.
0, 0 plus 1, or like either 0, 0, 50% of the time, or no, now I messed it up. 0, 1 or 1, 0.
Exactly. So either you measure the first qubit to be in 0, and then you flip qubit 2, so you get that in 1, so you get 0, 1. Or you measure qubit 1 to be in 1, and then you don't flip qubit 2, so that stays in 0. So 0, 1, 50% of the time, and 1, 0 again. And then if I run this on the simulator, I get a result. Which is, yeah, this 0, 1 or 1, 0 is basically the same probability. However, if I run it on one of the actual hardwares, it says error. So these conditional if, or these if statements don't seem to work for now on the actual hardware. Now, I did here for the MBQC then, same thing. So now I'm doing this 4-qubit circuit, define a quantum register, a classical register, it's 4 qubits, the quantum register. We make a circuit with these registers. And then first, I'm going to start the qubits 1 and 4 in 1. So I do X on them. And then I do Hadamard on the others. That was the initialization. Then we did these entangling gates. And then we did Hadamard on the 2 qubits to be measured, because we wanted to measure them in next spaces. And then I measure them, the first 2 qubits. And then I need to do some if statements. And you can use this function C underscore if, so some conditional if. And you are, what this means is that you do this operation. So you take the circuit and you do the operation Z on qubit 2 if the classical register is 1. Here I do X on qubit 2 if the classical register is 2. So why is this 1, 2, and 3 here?
Do we have to just convert to binary?
We have to convert to binary. It's like, I wanted to say, I wanted to condition it on this outcome on one of the measurements, but I couldn't get that to work. What only works is that if you use the whole classical register and say that that's a binary number, then you have to just fill out all the different cases here. So we have 4 cases. We are measuring 2 qubits, and we can get 0, 0, 0, 1, 1, 0, or 1, 1. So they correspond to 0, 1, 2, 3. And we need to see what operations would you do in each of these cases.
I see.
And then at the end I measure then the other 2 output qubits. So then it looks like this, the circuit. I do the initialization, entangling, measurement on the first two, and then here I do, so here you can see there's a 1, 1, 2, 3, 3. So these are different operations conditioned on different states of the classical register. And then when I run it on the simulator, so remember now that the upper digit here, so the last digit, if you read from left to right, the upper digit here is qubit 0, next one is qubit 1, qubit 2, qubit 3. So we are measuring qubit 1 and 2, and those we can get 4 different results, 0, 0, 0, 1, 1, 0, or 1, 1. And we were using the input states 1, 1, and for the C naught that should lead to output state 1, 0, we flip. And we see that we get 1, 0 for qubits 3 and 2 here, 1, 0, 1, 0 in each of these cases, so the feedback is working. But then when you try to run it on one of the actual hardware, you get an error. Okay, and then to really see that this is working, you would have to try with other input states as well. This is the basic. So, what do you think? Is it easy to program a quantum computer?
Super easy. They still have to fix some bugs and
Yeah.
stuff, but very impressive that this can be done.
Yeah, it's nice. You can really play around with. Okay, so we want to do this very particular thing with a conditional measurement, and it's not quite implemented yet.
Yeah.
It's something you also need for teleportation.
Yeah.
So it is quite important. It will be possible in the future.
But like since this all things are open source,
Yeah.
you could probably open up the code and either do it yourself, or a lot of people want this to happen. It can be.
Yeah, I don't know. I mean, if it's open source, I don't know even if you could tweak stuff here, if they would let you tweak stuff that goes to the hardware.
Oh yeah.
So instructions that go to the hardware might still be off. They are probably off limits. But do you think this is how you will program a quantum computer in the future?
No,
No?
that's impossible. That's just a basic C note.
Yeah.
If you want to run it.
Oh yeah, I mean the C naught in MBQC, I don't know if we'll use that like MBQC, but this interface like the Qiskit here, do you think this is how people will program a quantum computer in a few years?
Possibly if we can group stuff into like subroutines, because I don't wanna like have to take all these details every time I wanna do one simple, well, C naught or whatever. But if I can do that once and then just kind of reuse that every time, well then maybe.
But then that's like someone has to write a quantum compiler.
I think somebody is doing that.
A lot of people are writing different compilers, I think. But you need, I think you will need some higher level language than this.
Yeah, this is more low level. But that's an engineering problem, I guess, that will be fixed once we have.
Yeah, well, I don't know if it's even an engineering problem, it's more of a software engineering
Software, yeah.
problem. Yeah. It doesn't have anything to do with the hardware even.
Software engineers.
Yeah. Any other comments or thoughts? questions on programming quantum computers?
It would be nice if people just need to put their problems on the website and there is a mapping automatically happening.
Yeah, I mean, so I mentioned on Tuesday that D-Wave, they have sort of a compiler for a mapper for problems. So you can take your optimization problem, they feed it into this QB solver, what they call it, and they will sort of map it to something that they can do on their machine. So yeah, I think there are a lot of steps sort of once you, even if you have the qubits all there and you can control them and so on, there are many steps in the software stack that need to be worked out. Okay, I think this sort of concludes the computer exercise. I'll be around if you want to see if you can get this conditional if working. And then I will be sending out an email with a short survey about the computer exercise, because this was also part of I'm taking this course on pedagogical course where I have a project, so I have prepared some stuff for this computer exercise. I need to evaluate things. So I would be very happy if you could take 1 minute to answer some short questions.
You will email it out? Or?
I will email it out.